All right, hello everyone. This is 15.9. In this pre-class video, we're going to move to integrating in spherical coordinates. So we've already talked a little bit about spherical coordinates kind of back in chapter 13, a section that I had labeled 13.9. So if you need to review that, please go back and take a look at this. But let's get started. Just kind of a review that we can sketch things like phi equals pi over 4 or rho equals 2 cosine phi. And similar to the last section, 15.8, where we did this first in an RZ half plane and then moved to space, a similar trick can be done here. So let us recall in the RZ half plane, something like this. So R is positive. That's why it's the half plane rather than the full plane. Here's Z. Remember, for spherical coordinates, these come off the positive Z axis. So when I say something like phi equals pi over 4, we're going to have a picture that looks like this, where again, that phi value, how much it comes off of the off of the Z axis, right? This case is equal to pi over 4. So pi over 4, as we know, is 45 degrees. So something like that is about correct. We can also take this and spin it around, right? Like we do typically with these RZ half plane things, and we get a picture in space. So if we think about this for a second, and I draw it in space, X, Y, Z. And we, again, take this line, spin it around. Maybe I can even make it a different color so it looks different than my axes here. Spin this around, we're going to end up getting, we spin it around, a sort of cone-looking shape or a half cone, which is indeed correct. So this phi equals pi over 4 is the shape of a cone. If you'd like to go ahead and maybe verify this, well, there's a couple of ways that we can go about this. Maybe one of my favorite ways is to go ahead and apply a tangent to both sides. So if I write down tangent of phi is equal to tangent of pi over 4, that's the same thing as 1, of course. Then we can go ahead and multiply maybe by cosine on both sides. Remember, tangent is the same thing as sine divided by cosine. So that's going to give me sine of phi is equal to cosine of phi. Oops, I forgot my S there. And now we can multiply by rho on both sides. So rho sine phi, rho cosine phi. And as you remember from maybe the conversion equations, this is the same thing as Z, and this is the same thing as R. So this is a nice straight line. R equals Z. And moreover, this is the same one that we had in our last pre-class video in 15.8, where we saw that, yes, this indeed was a cone. All right. I'm worried I probably didn't leave enough room for myself, so I apologize. I'm going to cheat using technology a little bit and just shrink this down. Oh, maybe it will let me. Hard to say. I think I have to move it first. No, shrink. There we go. Okay, so that's half of it, right? I also wanted to graph rho equals 2 cosine phi. First, again, in the RZ half plane, then in space. So if I do this, rho equals 2 cosine phi in the RZ half plane over here. We can think about plugging in different phi values, right? And rho, again, is this kind of three-dimensional radius. It tells us how many steps we need to take away from our origin. Okay, well, if I go ahead and, for instance, and I plug in phi is equal to 0, phi is equal to 0 is going to give us rho is equal to 2, cosine 0 is 1, so therefore we get just 2. So therefore we need to take 2 steps, right? When I'm looking in phi equals 0 direction, that is straight up, because again, phi comes off the positive Z axis. I need to take 2 steps out, something like that. In fact, let me draw this a little bit bigger. Here's 1, here's 2. There we go. Okay, now if I go ahead and continue a little bit farther, for instance, if I do phi is equal to pi over 6, why not? Then I'm going to get rho is equal to 2 times, and cosine of pi over 6 is going to be root 3 over 2. So around root 3, which is 1.7-ish. So here's 1, here's 2, 1.7-ish, about right there. And we can do this a few more times. If we were to look in the pi over 4 direction, right, we would have root 2, which is going to be around 1.4-ish. So a little bit closer here. If I do pi over 3 direction, we're going to have 1/2 times 2 is 1. So something like this. And if you do phi equals pi over 2, it is this direction here, cosine of pi over 2 is 0. So 2 times 0 is 0. So we end up getting this shape right here. If you were to keep going, by the way, you would end up getting negative rows, negative radiuses. And again, remember, we're not allowing for really negative radiuses in this class. We don't need them. And so once that becomes negative, that's where you ought to stop. So for instance, if you were to try to plug in 2 pi over 3, or 3 pi over 4, stuff like this for phi, you would end up getting a negative row value. And so we don't allow for that. We don't consider those. And so this is where we're going to stop. So if I take this and I spin it, that is, I'm making a picture now in XYZ space. Well, spin that around the z-axis, we're going to end up with something that looks like a sphere, right? We have basically a circle that's a half circle that's sitting right on top of this XY plane, right, where z is equal to 0. And again, we've spun this around, and so we're going to get a sphere. So this is indeed a sphere. So we can graph this fairly quickly, again, using the RZ half plane in order to get an idea. And just like I mentioned in 15.8, when you get going with these, right, you can't just do them all in one picture sort of deal. If you want to just pen these axes, X's and Y's right here and spin it around. Again, the drawings are mostly for you. And so if you're happy with this, by all means, this is a good way to go. Okay. Again, just a reminder, similar to 15.8, all of this works so long as you don't have surfaces that depend on theta. You need to allow theta to be free, and that, again, kind of spins around the z-axis. And so, yeah, make sure that they don't have thetas in them. Otherwise, this trick doesn't work, and you have to kind of graph them out by hand very carefully. Okay, next thing that I want to do is calculate out the Jacobian for spherical transformations. This is going to take a minute. But for spherical transformations, remember we have x is equal to rho sine phi cosine theta. We have y is equal to rho sine phi sine theta. And finally, we have z is equal to rho cosine phi. So if we go ahead and we take our derivatives and put those into a nice matrix here, I'm going to try to start it right here, do my best. Okay, let's get to it then. Take some derivative. I'm going to start off by always taking the derivative with respect to rho. So the derivative of x with respect to rho will be sine phi cosine theta. Y with respect to rho will be sine phi sine theta. And z with respect to rho will be cosine phi. Okay, so those are all my derivatives with respect to rho. Now let's do with respect to phi. So I'm going to have rho cosine phi cosine theta when I take the derivative of x with respect to phi. I'm going to have rho cosine phi cosine theta when I take the derivative of y with respect to phi. And finally, I'm going to have negative rho sine phi when I take the derivative of z with respect to phi. And finally, I'm going to take the derivative with respect to theta. So I'm going to have negative rho sine phi and sine theta. Positive rho sine phi, and the derivative of sine is cosine theta. And finally, there are no thetas, so the derivative is going to be 0. It's constant with respect to theta there. All right, so now I've set up my Jacobian. Now we're going to go ahead and set up when we actually have to take the determinant here. So we're going to have a lot of stuff. And again, I'm kind of working my way across this first row. So I'm going to have a lot of stuff. And the first bit here is going to be sine phi cosine theta. Okay, as I work next, we're going to have minus. In fact, just because this is so long, I'm going to kind of start a new line there. And the next one is going to be rho cosine phi cosine theta. And then finally, we have, oh, there's another minus sign. So I'll go ahead and put that up front here. And this is going to be rho sine phi sine theta. Okay, now for each one of those, remember we have to calculate out the 2x2 matrix minor. And so if we cross off this first row and first column, let's see, I'm going to be multiplying by 0. That's nice. And when I multiply in this direction, so I'm going to have minus a negative. So plus rho squared sine squared phi cosine theta. Okay, that's one down. Now when I go to the next bit, let's see, we're going to have 0 minus, and let's see, a singular row here, sine phi cosine phi and cosine theta. And then finally, when I do the last one here, we have negative rho. This one I feel like I'm going to need some more room. I'm going to go ahead and cheat, move this over. Let's see, negative rho sine squared phi sine theta minus, and then when I do the other diagonal here, we're going to have rho cosine squared phi cosine theta. All right, so that right there is the determinant of this. And now we need to simplify for a little bit. All right, so the first thing that I notice is that every single one of these terms has a rho squared, right? When you distribute that last one, right, you get rho squared. So everything has a rho squared. So I'm going to go ahead and factor out rho squared from all of this stuff. And then I'm going to kind of expand a little bit and see what we get. And so for this first bit here, it looks like we have sine cubed phi cosine squared theta. Next up, we have minus a negative, so that's going to be plus here. And let's see, let's try to keep all of our phis up front. So I'm going to do sine phi cosine squared phi, and then I have cosine squared theta. So again, that was this bit right here, just trying to simplify, and I'm going to write my phis before my thetas just to kind of keep some sort of sanity here as best as possible. And then let's see, all of these negatives kind of cancel out because again, you would have to distribute this negative. And so it's all going to be positive here. That's quite nice. So let's see, plus, let's see, I'm going to have sine cubed phi sine squared theta. That's after I distribute this stuff to my first term. And then in my final term here, I'm going to have sine phi cosine squared phi sine theta cosine theta. Man, these thetas and phis are going to kill me here. All right. Well, it's something. Now I'm hoping that there's a fair number of like sine squareds plus cosine squareds equals 1 sort of deal. But again, we have to make sure that the variables need to be the same. So this can work with thetas and it can work with phis, but you can't mix and match, right? You have to kind of stay the same, either stay with thetas or stay with phis. Oof. Actually, at this point, I was going back and double checking my work really quick. And I found out when I went and I took, oops, I have my eraser still. When I took my derivative of y with respect to phi, right, I wrote cosine of theta rather than sine theta. Probably you guys caught this and have been yelling at the screen that this is going to cause issues, and it indeed has caused issues. And so I need to go back and kind of everywhere that I had cosine phi, cosine theta, I need to go ahead and swap that out. So let's kind of go back here. That one, it didn't come up because we had 0 when I cancel out the second row, it doesn't come up. So just here at the end, actually, when I do this multiplication out, this should be sine of theta. There it is. Okay. So when I distribute now, right, I don't actually have a cosine of theta here. I have a sine squared theta. And my claim is that's exactly what I'm looking for. That'll make things work out a lot nicer now. Okay. So again, I'm going to be looking for groupings of sine squared and cosine squared with respect to either phi or with respect to theta. For instance, I noticed right here, oops, with these two, that if I was to factor out sine cubed, I would have sine squared plus cosine squared of theta. So that means this is going to be the same thing as sine cubed phi, and the cosine squared plus sine squared of theta will be the same thing as 1. So that's one way that we can go ahead and simplify this. Another way that I saw that we can simplify this, notice that for these other ones, for instance, these terms 2 and 4 here, they both have a sine phi, cosine squared phi. And so if you factor that out, sine phi, cosine squared phi, what's left over is cosine squared theta plus sine squared theta, which is equal to 1. All right, so we've simplified quite a bit. We still have our rho squared to multiply by all of this. And lastly, if we go ahead and factor out a sine of phi here, so rho squared sine of phi, what we're going to be left over with is sine squared phi plus cosine squared phi. And of course, this is going to be equal to 1. So after all is said and done, I know it's a bit complicated, right? We get rho squared sine phi. This right here is the integration factor that we need to make sure to include when we switch from Cartesian into spherical coordinates. So just like in cylindrical or polar, we needed this extra r. Here, we need this rho squared sine phi whenever we switch from Cartesian to spherical. All right, so that means if I wanted to write this down in a nice theorem, we need to switch our function, of course, into the correct independent variables, rhos, phis, and thetas. And then that extra integration factor here is going to be this rho squared sine phi. And that's how we're going to transform, again, from Cartesian to spherical. With that, why don't we go ahead and do an example problem, calculate out the average height of a point inside of the hemisphere with z is greater than or equal to 0. So if I'm interested in the average height, well, remember, if we want the average of some function, and we're at a point inside of the hemisphere, that means that this is a three-dimensional structure, right? So I want 1 divided by the volume of my region, I'll use E, times the triple integral over this region. And the function that we're interested in, right, whatever this f function is, well, we're interested in finding the average of the height. Well, that means that the height, of course, is given by the coordinate of z. So this right here is what we're trying to evaluate. Of course, we remember how to find the volume of a hemisphere. It's just the 4/3 pi r cubed sort of situation for a sphere. That's the volume of a full sphere. If you want a hemisphere, of course, you multiply that by 1/2. And the radius of our sphere is 1. So this would be 1 cubed, which is, of course, the same thing as 1. So the volume here is going to be 2/3 pi. So we can go ahead and maybe swap that in the next line here. So this is 2/3 pi is the volume. And now I want to go ahead and integrate z over this region, right? Over this hemisphere with z greater than or equal to 0. Okay, well, well, first of all, we're inside of a hemisphere, so kind of spherical probably should be calling out to us a little bit that, hey, maybe integrating this with respect to spherical coordinates would be a good idea. We need to transform instead of z's, we need rhos, phis, and thetas. Luckily, we know a transformation equation. Z is the same thing as rho cosine phi. So we can go ahead and swap out everywhere we see a z. We can transform it into its equivalent in spherical coordinates. And now if we want to swap this into spherical, right, we need this extra rho squared sine phi. So this right here is this extra integration factor that we always need to have whenever we swap into spherical. We're going to integrate with respect to rho, phi, and theta. And now we need to spend a little bit of time thinking about our bounds. Remember, this right here is the same thing as a sphere of radius 1, or if you'd like to, you can put this into spherical coordinates by saying rho squared is equal to 1, or take the square root, and that's going to give rho is equal to 1. If we'd like, we can go ahead and sketch this sort of deal. So if I want to sketch this maybe first in the RZ half plane, remember rho is this three-dimensional radius from the origin. So, and another way to say that, right, if you wanted to, is you could take x squared plus y squared plus z squared equals 1, aka rho equals 1. And you could group this, right? X squared plus y squared is the same thing as r squared. So this is r squared plus z squared equals 1. That's a circle of radius 1 centered at the origin. So something like this. But again, you could also think about just plugging in different phi values, right? And for all of your different phi values, they're just going to keep on giving you out rho is 1. Take a step of 1 away from the origin. So if I plug in phi equals pi over 6, or phi equals pi over 4, or phi equals pi over 3, right? All of them are going to say take 1 step away from the origin. And so we're going to get a picture that looks like this. If I was to take it and spin it around to get a picture in XYZ space, right? Of course, we get our classic sphere, which we already knew that was going to look like. The problem is, right, we don't want the entire sphere. We really only want the top half of the sphere. So we could have also considered this a little bit earlier, right? We have an extra prompt here that says that z should be greater than or equal to 0. So notice that we have to take both of these things into consideration to get the fully correct picture here. So you're not going to include the pieces where z is less than 0. So if I was to think about this, right, for a spherical setup, maybe the first thing that I'm thinking about is, well, I need to integrate with respect to rho. How do I enter and how do I exit? Well, as soon as I take the tiniest step off of the origin here, right, I am already inside of the hemisphere. And I keep on going until I exit through this sphere of radius 1. So that means that I'm going to be entering in through rho equals 0, the origin, and I'm going to be exiting through the sphere of radius 1. Okay, now I need to be thinking about my phi values next. So for phi, remember phi comes from the positive z-axis, goes downwards. So if I was to positive z-axis goes downwards, notice that if we're pointing straight up, we are in the hemisphere. That's good. And all the way down to about 90 degrees, right? If phi goes down to about 90 degrees, that's all fine. But then once it goes past that, right, if we were pointing in this direction, right, there is no hemisphere down there. And so the correct setup here will be phi ranges from 0 to pi over 2 or 90 degrees. And then lastly, for our thetas, notice that there are no restrictions on theta here. So either if you were to look at rho equals 1, or if you were to, by the way, with z equals 0 being a boundary, if you were to spend a little bit of time, z equals 0, we could write that as rho cosine phi equals 0. Divide by rho on both sides. That's going to give us cosine of phi is equal to 0. And that tells us algebraically here that phi is equal to pi over 2. So this is where phi equals pi over 2 shows up in the equation. So you can either think of it graphically and draw a picture and kind of look at it and reason that way, or you can take the equations and work on things algebraically and come up with the results that way. So again, you kind of see the rho equals 1 and the phi equals pi over 2 showing up in the bounds. But notice with these, you don't get any restrictions on theta. There are no thetas. And in fact, from the picture as well, you can see that you want your theta to include the entire 0 to 2 pi. It needs to go all the way around, right? There's the hemisphere exists in every direction as we move left and right. And so therefore, we want our thetas to be 0 to 2 pi, kind of the old classic bounds here. Okay. Well, with that, let's go ahead and integrate. This is the main reason kind of back in, 15.2 originally, kind of we brought up this idea that when you had many integrals, and we saw this a little bit in 15.7 as well, right, that sometimes that you could split them up very nicely. So notice that you have multiplication, you have a function with just rows. For instance, if you multiplied that all out, row and row squared, that would be row cubed. We have a function of just fees. So cosine phi sine phi. And you have a function of just thetas. Well, in this case, there really aren't any thetas. You can always multiply by 1 if you'd like. And so you can do that. And now you have a function of thetas. And so spherical is kind of the main case where you really end up splitting up your integrals. This is a huge time saver. And I would really recommend it, for the upcoming exam and for the final and all that sort of stuff, just because it does save a great deal amount of time. And so if you're interested in having more time on the exam, this is good strategy here. So, okay, thetas again go from 0 to 2 pi, fees go from 0 to pi over 2, and rows go from 0 to 1. In fact, when we have fractions over fractions like this, why don't I go ahead and multiply by the reciprocal and have 3 over 2 pi. Let's see, when I integrate 1, I'm going to have theta, because remember, we're integrating with respect to theta. Plug in from 0 to 2 pi. When I integrate this, it's a little u substitution. In the interest of time, I'm going to go ahead and write down the answer, but feel free to take as much time with this as you need. Certainly, I can kind of guess and check as well. If I take the derivative of this, the 2 will come down, cancel with the 1/2, and leave the inside alone. So I'll have a sine of phi. And when I take the derivative of sine, I get cosine. So yes, we indeed get exactly back to where we started. And then finally, I have 1/4 rho to the 4th power from 0 to 1. So this allows our integrals to go very, very quickly. And so when I go ahead and plug these things in, well, this is going to be 2 pi minus 0. When I plug in pi over 2, I'm going to get 1 times 1/2. And when I plug in 0, I'm going to get 0. So if you'd like to, you can write the minus 0, but it doesn't really do a whole lot. And then finally, when I plug in 1 here, I'm going to get 1/4. 1 to the 4th power is just 1. And when I plug in 0, I get 0. So something like that. We can see there's a little bit of canceling that's going on here, canceling out a few things. And so we get our final answer of 3/8. So again, if you think about heights here, the smallest height is going to be at z equals 0. And the largest height for a sphere of radius 1 is going to be at a height of, sorry, I'm getting ahead of myself, is at a height of 1. Again, it's a sphere of radius 1. So of course, we're expecting an answer for an average height to be somewhere between 0 and 1. In this case, it kind of indicates, right, that, 1/2 right here would be maybe a naive guess, right? If you had to guess something, maybe 1/2 sort of deal. But you can kind of see that the sphere is fatter near the bottom, right? There's more points, near the bottom. And so it's maybe not surprising that we get out an answer that's less than 1/2, just because, again, there's kind of more points. And so you would say the average height is going to be a bit smaller than 1/2. All right. Thank you so much, guys, for watching. Let me know if you have any questions, and I'll see you in class.